welcome to this lecture. In the previous class, we were talking about the steady state technique for measuring the heat transfer coefficient or the J and F coefficient for the plate fin type of heat exchangers, and there we have seen that the steady state technique, in the steady state technique we have the condensing steam and the air is getting heated up and there is a heat transfer between the fluid and this condensing steam, and air gets heated up and it picks up the heat from the condensing steam, and the condensing steam gets condensed, and we have made two assumptions that the heat transfer coefficient the temperature on the steam side will have a constant wall temperature, it will be maintained at the condensing steam temperature, whereas the air will be getting heated up from its inlet temperature to the exit temperature. So, depending on this relation of the basically we assume that here the CR or the heat capacity rate ratio is 0, because the condensing steam is having a very high heat transfer coefficient, and we have this CR equals to 0, and the heat capacity basically is very high for the condensing steam. So, we have this high this because of that one we have this CR equals to 0, and we have a constant temperature for on the steam side. Now, the air is getting heated up from the T in to the T exit. So, now we in this condition what we do is we measure the inlet temperature, we measure the exit temperature of air, we measure the flow rate of air, and we would be able to calculate the condensing steam temperature, that is already known depending on the pressure of the saturated steam, and exit and inlet and the exit of the air temperature is measured. So, we have an idea about the NTU, and once we know the NTU, basically this is UA by C mean. This C mean is nothing but the air heat capacity. So, this C mean is known, and we know that NTU, that is equals to NTU. This NTU is basically this from this relation we have already calculated from the measured value of the inlet and exit temperature and the steam temperature, saturated steam temperature. So, we can understand that we have the knowledge of UA. So, once we know the UA, as we have seen in the previous slides, that because of this I am sorry, this is in the previous slides we have seen that this 1 by UA part, this 1 by UA part is related to the known heat transfer coefficient. It is also known wall resistance, but already we have an estimate of this UA, and now we would be able to calculate this unknown heat transfer coefficient, where we have put the test surfaces on this side. So, this is how we measure the heat transfer coefficient in the plate fin type of heat exchangers in the form of the heat exchanger, and moreover in the same way we also calculate the from the inlet and the exit pressure drop we measure, and from this differential pressure measurement we can correlate it to the different losses. Here we have the core, this is the core friction part, and then we have the entry and the exit loss, as we have discussed earlier during this plate fin type of heat exchanger pressure drop calculation, and this is the duct loss. This air, we will find that it is flowing through our duct, and that is also giving some kind of heat pressure loss, and that is also taken, but these parameters will be generally very small as compared to this core pressure drop. So, these parameters are generally known. We have the known value of the Ke and Kc, and we know how to estimate that, and we have the duct size known and the friction factor of the rectangular duct or square duct that will be known, and from there we would be able to estimate all these parameters, and we can now calculate this friction factor corresponding to the pressure drop where we have the test surfaces. So, basically we measure the pressure drop and then from there we calculate the friction factor using this relation. If someone wants that we do not need that much accuracy, we can easily neglect this term. One can just concentrate on this part and one can find out the friction factor from the pressure drop calculation. But if someone is looking for an accurate measurement of the friction factor, then one has to take care of all these the parameters given in the equation. So, now these are the two parameters we will be calculating from the heat exchanger from the test setup, and we have already talked about this part, and this is the steady state test setup. It looks a bit complicated, but we will be trying to separate it out. Here we find that we have a heat exchanger, this is the heat exchanger and this is where we have the heat exchanger which we want to test, and the test surfaces are there on the air side and on the steam side. So, we can understand that we have two circuits here, one is generating the steam and the other part is the air, and this is the airflow path, and we have a blower on this side, we have a flow control valve here, and this is a data acquisition system to monitor the temperature and pressure at the different points. So, here we will first of all separate it out into three components. One is the air side, one is the steam side, and separately we need to look into this particular design of this heat exchanger for this to understand this steady state heat transfer technique. So, this is what is the airflow system. So, here we have the again a bell mouth air entry, then this is the test section, here we have the float straighteners, this is the heat exchanger, this is generally in case of plate fin type exchanger, depending on the geometry, most of the time you will find that this test section is a rectangular cross section, and here this is the blower, and this transition from rectangular to circular is generally done at the entry of the blower. This is the motor of the blower, and here we have at the exit of the blower we have a flow control to test it at the different Reynolds number. So, this is what is about the airflow system in general, and this is the air duct that has been used in this test setup is typically of this dimension, and the total length is 6.1, whereas the blower capacity is something like 9,500 meter cube per hour, and for a 1.06 water gauge pressure drop or the pressure head available with this blower, and its motor RPM and the power is 75 HP. So, basically this blower capacity and this what is called this air duct configuration depending on the test setup and the RE values that you need, that will dictate these terms, or the size of the blower will be basically governed by the type of heat exchanger test surfaces you are you are going to test them. So, here we have taken this kind of dimensions, overall dimensions for this airflow system. So, here some of the pictures, this is the heat exchanger that has been tested in this test section. This is the flow straightener that has been used in this particular So, this is the flow straightener section, this is the exchanger what is here, and this is flow control valve which has been placed in this position. So, now we go to the steam system. This steam system is basically we use in the laboratory system we have used a non-IBR diesel fired boiler. It is a package type of boiler which gives nearly about 480 kg of dry steam and at a pressure of 15 kg per centimeter square. So, this is when we want to take it to the heat exchanger, we want it at a saturated condition, but it is very difficult to maintain it at a saturated condition, and moreover when it is the air is flowing through this, some of the steam will get condensed and it may create some kind of two phase flow in this region on the steam side. So, that is why we it is allowed basically this is I have forgotten to tell you that this is the method used by Case and London, and we have adopted that technique. Sometime this state technique is also called the Case and London technique, and here we maintain this steam at nearly about 4 degree superheat is maintained at this point, and it is nearly about 1.4 to 1.5 bar. So, here we have the steam at 15 bar pressure nearly, and from there we will be reducing it to 1.5 bar. But if we want to do it in a single stage, we that there would be very large degree of superheat, we will not be able to control it at this point. So, what we do is that we reduce it in two stages, one by the time it comes from this boiler to this point through the phase separators and all, it will be available at a pressure of 10 bar. So, from 10 bar we reduce it to 3.5 bar, and that will give you some degree of superheat, and that superheat is removed. In order to remove that superheat, we mix it with the water. So, this water will be mixing with this superheated steam, and this excess water will be again separated out, and finally, we have the saturated steam at 3.5 bar. Once we have this saturated steam at 3.5 bar, we reduce it to 1.5 bar, and with this degree of superheat of about 4 degree centigrade, we send it through this heat exchanger. So, when it comes out from this exchanger, this steam at 4 degree centigrade superheat will be lost, and along with that there will be this condensation of the steam. So, mostly we can assume this will be prevailing at a temperature of Ts corresponding to the saturation temperature, saturation pressure of 1.5 bar. So, the steam that is used in this process is about 3 to 6 times of the part that is getting condensed, and this is excess steam is used because we do not want any accumulation of the steam or the condensate on the steam side, because any condensation process on that one will reduce the I mean if it is getting accumulated, the steam getting condensed, and that condensate if it is accumulating on the steam side surface, that will reduce the heat transfer coefficient. So, we want a drainage of that excess condensate or the condensate, and that is why we use the excess steam, and that excess steam will take care or remove the condensate from that heat from the test channels or the on the steam side. So, this condensate is again collected, and then we measure it, and then we subcool it, and then we collect this condensate. So, that gives you basically an idea about the energy balance, and this excess steam will be blown out. So, this is about the test section or the steam system, and then we have the heat exchanger. this needs a special attention because these exchangers are to be designed carefully, otherwise that is going to give you erroneous results. And the recommendation is that the NTU is it should be nearly about 1 to 3, and there is a reason for that. If we are going to use a very high NTU exchangers, we can expect that that NTU relation we have shown as 1 by 1 minus epsilon, and that that it is like the T, it is at T s, and the inlet temperature is this is T in and this is T out. So, this is coming at T in and it is moving out at T out, and this the steam side temperatures are remaining constant. So, now if it is such that the heat exchanger NTU is very high, we will end up with a case that this T s minus T out will be very small, and there the probability of error will be it can be shown that this error estimation will be much more. So, we design the exchangers so that the NTU remains within 1 to 3, and the blow steam to condensate ratio is, as I told you, that it has to be nearly about 3 to 6. So, the blower capacity it has already been decided depending on the Reynolds number and the pressure head available with that kind of blower, and out of that available pressure head, only a part of this one will be available for this heat exchanger core. This is the only heat exchanger core. This is the length of the exchanger core. These are the sides of this is the fin. These are the fin which we are going to test. These are the fins which we will be testing, and the pressure drop for that heat exchanger core of length L A, we have only allocated 0.7 or 70% of that 1 meter of the water column, or 70% of the pressure head available with this blower will be allocated for the core pressure drop, and rest of it will be through that what is the flow straightener and duct and etc., that will be consumed by that remaining part. And we have assumed that 480 kg of dry stream, and depending on this assumption we have calculated the heat exchanger design has been done. So, starting with the NTU, we first calculate from this relation we calculate the exit temperature, and from there we calculate the mean values and the based on the mean temperature. From there we already know the fin details. So, from there we can calculate the hydraulic diameter etc., and we can estimate the pressure drop. So, once we know the pressure drop, we calculate the other G and F correlations we use here. We need to have a rough estimate of the heat transfer coefficient and the pressure drop for the test surfaces, and from there we can check whether this it is within that Reynolds number region, or whether it is conforming to our flow rate, or whether it is that maintaining that steam to condensate ratio within 3 to 6, and accordingly we will be finalizing the length of the heat exchanger. So, once we know the heat exchanger length, we can test it, put it in the test section. This is the pictorial view of the test setup. This is the boiler, and then we have this is the boiler. These are the different pressure reducing station, pressure reducing station 1, 2, and then we have this steam coming like this. This is the heat exchanger. The steam is flowing like this and getting condensed, and then it will be following this one. There is another test section. This is we have removed that part. This is where we have that bell mouth. This has been removed, and to show it the heat exchanger inside. So, we have another rectangular test section like this on this side, and then the air will be flowing. This is an induced type one. So, we have this is blower, and this is the valve, and the motor is on the back side. So, this is the pictorial view of the test setup. So, here some of the instrument part, I mean this is basically a PRT, a single PRT platinum resistance thermometer, and we have measured the inlet temperature at a particular point, but for the measurement of the exit temperature we had to measure it at different locations because we expected non-uniformity in the temperature region in the exit of this heat exchanger. So, that is about the measurement part. Then we have also measured the flow rate at different locations, I mean at the entry of the air flow. And then once we develop the test setup, it is very important to calibrate the test setup. So, for calibration of the test setup, what we need a test surface for which the heat transfer coefficient or the pressure drop is known. So, initially what we did is we calculated the friction factor and this is the test surface which has been tested by Case and London, and we had the data for the Case and London, and to test that we have our test setup correctly built, we have measured the pressure drop at different time. And what is important for any test or the measurement or thermal measurement, thermohydraulic measurement is the repeatability test. So, we have done these experiments time and again, and we have calculated or we have seen that it is conforming to the values given by the Case and London. So, this is basically the cold test, or this is where we did not use the steam, only the air was flown through the heat exchanger test surface. So, this is how we have measured the friction factor, and then in presence of the steam we have generated the friction factor and the also the heat transfer coefficient or the J factor. So, here we can understand that the J factor and the friction factor are very closely related, or they are very I mean they are almost following the results given by the Case and London. So, this calibration will be able to eliminate what is called the systematic error or the any experiment if we are performing, it contains two type of errors you may be knowing. One of them is the systematic error, another one is the random error. So, basically what we try to understand is, or try to calculate, is the random error associated with the different measurement, whereas the systematic errors are eliminated by this type of calibration of the test setup. So, that has been done first, and then subsequently we have tested the different heat exchanger surfaces. So, this is the random error estimation, and these are the type of expression that we use for calculation of the random errors. This is if there are x number of, say, n number of parameters x 1, x 2, x n, then we have the error associated with that measurement will be say delta r, and delta r will have a component I mean this is the delta x 1 associated the error associated with the x 1, and this is delta x 2 associated with x 2, and so on, and it keeps on adding, and the errors are additive. So, the total error associated with this measurement will be delta r, comprising of all the individual errors of measurement. But another estimate of this pressure, I mean error is given by this relation by Moffat and all. So, this is how we estimate the error, the random error associated with any kind of measurement. So, when we talk about the mini channel, it is slightly different. You may be expecting a similar kind of test setup, but here we go for a power supply and we heat it up from the bottom, and it is not like we send the steam in this one, because this you can understand the dimension of these surfaces, and these surfaces are very small in size. This is about 0.25 mm channel, and here we do a different type of test where we calculate the flow rate or we simulate the flow using syringe pump, and it is through which the syringe pump will allow the water to flow in through these small channels, and we measure the pressure drop across this channel, and then we also put some known amount of heat through the power supply, and then we estimate the heat transfer, and accordingly we calculate the heat transfer and the pressure drop for these channels. So, this is the kind of test setup we use for the sample holders, and this is the type of experimental setup where we have the syringe pumps, data acquisition system, then this is the power supply, and like that. So, in case of foam heat transfer, a similar type of experimental setup is used, but again this will vary from time to time, and here just we will have a glimpse of this test setup. This is the rectangular test section. So, here it is heated up from the top and the bottom, and this is where we have the aluminum metal foam within it, and we measure the it is supposed to be covered up when it is in the heated condition, but for the video recording we have removed that this cover, and they are maintained at particular temperature. They are electrically heated up, and this is the flow measurement device. It is an inline flow meter, and it is measuring the flow rate, and you will find we will be showing you this is the air entry and this is the blower. The air enters from this end, and then it flows through this section, this test section, and then it finally comes out like this. So, this is the data acquisition, and then we calculate the heat transfer coefficient and the pressure drop. So, when we make the heat exchangers finally out of these test surfaces, we have a different type of test setup for measuring the performance. So, this is one of the test setup where we measure the heat transfer performance or the heat exchanger effectiveness. So, here also we put the air this water flowing through this one, we allow the water to flow through this channel, then we put either heat in it, and then this is the other fluid or the same fluid, but with a different temperature, and then it is flowing like this in a closed loop. So, this is the cold fluid and this is the hot fluid exchanging heat with each other. So, here we are putting heat, and from measurement of all these temperatures we would be able to calculate the efficiency, overall efficiency of this heat exchanger. So, this is about the test setup of the heat exchanger. Thank you for your attention.